In this recording, we're going to begin our review for the Algebra 2 Regents. So the two sets of materials that we're going to need are our final exam review packet. This was for our Algebra 2 final exam, number one. And we're also going to need our eMath quizzes. So this is a packet that you have that has quizzes 1 through, I think there's 10 or 11 of them, maybe 12. Review quizzes. We're going to do select problems from each of those, and then I'm going to have you do the rest for practice. So specifically in this packet, we're going to start looking at our units 1 and 2 from last year. And we're going to pick out a few problems. This one, first problem, has to do with the nature of one-to-one, what it means to be an inverse, and then things like basic domain and range. So hopefully this will come back to you. We have a function here that we can't describe with an equation, but it's a function, right? It has exactly one y value for every x value, so that makes it a function. Question is it one-to-one? And I think we can say yes, it is. It's a one-to-one function because not only is it a function, it passes the vertical line test, but it also passes the horizontal line test. Our next question asks about an inverse. How do you graph an inverse? And again, the notation for inverse is this f with a superscript -1. So it's not an exponent, it's just expressing the inverse in notation. So what we're going to do is take each one of these points on the graph, each one of these significant points, and we're going to switch the x and y. So we'll find the coordinates and then just invert them. So I'm going to take each one of these points and switch their x and y. And now I'm realizing that the placement of that point could be a little better. Let's slide it over there. I think that'll work. Okay, so once we have those end points, those critical points plotted, we can just connect the 3 points. And then let's draw in the line of symmetry. Okay, that's part C. Identify the line of symmetry. Well, if you were to fold this, well, I guess I should have written the inverse name on there. I should. So let's call this one f of x, and this one inverse of f of x. If we were to write the graph, the line of symmetry, it should be this fold line that goes from corner to corner. And that's the line with a slope of 1 and a y-intercept of 0. That's the line y equals x. Now it asks for us to find a couple of values and state the domain and range. I think you're familiar with how to do these. Why don't you work out parts D, E, and F, and then play the recording when you're ready. Okay, so hopefully you found the value of inverse of f of 1. Okay, now I'm looking on this blue graph, so I'm going to where the x value is 1, and the y value for that particular point right there is -1. So that's what that's saying, the y value. Okay, that's what that's saying. And now the domain and range. So I need you to be familiar with both interval notation and set builder notation. So if you wrote it one way, write the other as well. Not that you would need to write both on the test, but you should be able to recognize both. Okay, so again, for the domain of the original function, it's all the x values. So I start here at -7, and I continue on this curve all the way to this point without breaking, all the way up to that x value of 7. Same for the y's. Continues from -5 all the way up without any place where it does not exist, all the way up to 5, and it includes the endpoints. Because I have solid dots on the ends, I use the brackets. Alternatively, so that's interval notation. Alternatively, we could have written it with set builder notation. X such that we have these conditions. And then finally your inverse. Well, the nice thing about writing inverses is the x's and y's switch, right? We should probably have made a note back up in here. How do you graph the inverse? Switch the x and y. Okay, so it's simply switching the x and y right here. The domain of the inverse is the range of the previous. And I'm realizing I made a little mistake up in here. This has to get fixed. This should not have been a -5. It should just been a +5. Let's fix that. All right, next question. Find the inverse of a function. Well, we said switch x and y, right? You would do that if you had to do problem A. You just switch the x and y for all the points. We're working on problem C, where we're given the inverse, and we want to find, well, what was the original function g of x? So we're going to switch the x and y. Well, there is no y. But what we can do is say, okay, let's turn this into a y equals. Okay, because we know that anything in function notation really refers to the y value. So the g inverse of x is the y value. And now we do need to switch the x and y. So switch their positions. Create some space over here. There's several ways to solve it from here. Why don't you get as far as you can and play the recording? Okay, so hopefully you did something with that fraction or subtracted 3 and then do something with the fraction. There's multiple ways to do it. I'm going to get rid of the fraction first by multiplying all terms by 5. Those divide to 1. Now it's going to be easy for me to get y by itself. That should have been a 15 on the end there. Oops. It's going to be easy for me to get y by itself by just subtracting the 15. Okay, in my final form, however, what I should do is express this in the proper notation. Because the original function was written as g inverse of x, this should become the inverse of the inverse is the original function. We have multiple ways we could check that, including graphical and substituting in values for x, figuring out what the y would be, and then subbing in that y value and seeing if it gets back to that original x. Okay, the next question we're going to look at is question 4, a factorization question. So if it says factoring completely, the first thing we always want to look for is the GCF. Let's make that note. Okay, always going to look for that GCF if it exists. So why don't you look for that GCF and play the recording when you're ready. Okay, so there's multiple ways to go about this. I'm going to take out that GCF of 3x first. I'm going to divide all the terms by 3x. So some people will write it right underneath each term. I'm not going to do that, but you can. Okay, now because we have 4 terms, a cubic polynomial with 4 terms, cubic because it has a 3 as the largest exponent, I'm going to think about factoring by grouping here. This can be done with or without a box. I'm going to use a box here because I've seen students be very successful with it. But it's not the only way. You don't need to use the box. Okay, so I'm going to place all 4 terms in the panes of the window. Okay, and now I'm looking to factor out a GCF in each row and column. So I'm going to start with the x cubed. I know that can be factored with x squared and x, so I'm going to look at x squared in the top row as the GCF, and therefore it's an x on the top, x squared times x, and over here, negative 2 as the factor that multiplies by x squared to produce negative 2x squared. On the left side, well, of course, it would be a negative 4. Negative 4 times x makes negative 4x. Just double check, negative 4 times negative 2 as a product of 8. That looks great. Now I'm going to keep my 3x. That's a huge source of error, is people just neglecting that 3x. That still has to be there. Okay, don't drop that 3x. But now we have factored out the cubic polynomial here, and we're going to write it in factored form, taking the dimensions from our box. To factor completely, you want to make sure that every factor is completely factored. I see a factor here, that this binomial, difference of two squares, that can be factored further. So go ahead and factor that further. Play the recording when you're ready. Okay, so hopefully you broke that down. Hopefully that's starting to come back to you. X minus 2 and x plus 2. The order of the factors does not matter, of course. According to the commutative law of multiplication, you could have changed the order here and you'd be fine. A way to check this: pop that into your calculator, pop the original in the y equals, of course, the original expression in your y equals, and then look at the table. If they agree, then they are equivalent. It's a nice little check. Next question. Number 5. It wants us to place this quadratic into what we call vertex form. This should be very familiar to you in terms of the effects of A, H, and K. Just coming off our trigonometry unit, you know a lot about what A does in terms of reflection and in terms of vertical stretching, as well as H shifting right and left, K shifting up and down. Okay, so we want to get it into that form so we can identify the transformations. Okay, so in order to get this into vertex form, what we're going to do is complete the square. Okay, completing the square works well when the A value is 1. So the first thing I'm going to do is sort of factor out that A value from each term. And you might say, well, that doesn't work well with a 25. You're right. I intentionally set it up so that it would be a little challenging, because we're only going to do one of these. May as well do one where everything's going to come up that could possibly come up. I'm going to use a square bracket here because there's going to be an internal parenthesis you're going to see over here. So for now, just factor out that A value, factor out that GCF of 3. Can't write and speak very well. And I guess just represent this 25 over 3 as a fraction. There's no point in turning into a decimal. Just like that. Now that we have this quadratic with an A value of 1 inside these brackets, what we can do is complete the square. We do it this way. We keep that 3 outside, and we're going to put in parentheses an x squared minus 6x, but I don't know what number I'm going to need to put here to complete the square, so just kind of put your parenthesis there. And I'm going to put the 25/3 outside. Okay. Let's go over here and figure out what number is going to be required to complete the square. It needs to be a square number so that we can factor it as a perfect square trinomial. So one way to envision that is, get some color here. So I've got an x squared, and I need to have equal dimensions. Okay, x and x, whatever the number is here, needs to be the same number that is down here. So I have a square, right? It needs to be the same. So therefore, I'm going to split that negative 6x into 2 equal parts, negative 3x and negative 3x. Again, doesn't need to be done with the box, but it can be. Now hopefully it's obvious to you, you need a negative 3 on the side and top. Well, therefore I have a square, x minus 3x minus 3. the only number that makes sense down here is a 9. I'm going to use a color. Okay. So I want a 9 to be part of this trinomial. I'll put it in red. Therefore, if I add it, I must also subtract it to keep everything balanced in the expression. Fine. Now what I have here is something that I can factor using a perfect squared trinomial. X minus 3 to the second power. There it is right there. X minus 3, x minus 3. Keep everything else the same, but just do some math over on this side. Okay, let's kind of think of negative 9 in terms of thirds. Let's call it negative 27 thirds. Okay? So therefore, that adds up to negative 2/3. All right? Put our brackets in. Still have that 3 out in front. Now it's looking really similar to the form we want, but I don't see any brackets in that form, in that vertex form. So again, distribute your 3 back in, and it's going to work out very nicely. We have our a value. And now 3 times negative 2/3 just leaves us with a negative 2. There is our very nice vertex form where we can see the values of a and h and k. Cool. Let's think about what those do. The turning point. Well, turning point of a normal parabola is 0, 0. So write down, what do you think are the coordinates of the new vertex? Okay, so this is a little tricky in here with the minus 3, but it's a good review. You would shift 3 to the right, so that gives us a x-coordinate of the vertex of 3, and 2 units down, so a y-coordinate of negative 2. Transformations. Well, we've got several things going on. We have to say the right order. Okay, the vertical transformations are independent of the horizontal transformations. We have 2 vertical transformations. We have a stretch of 3. We have a shift down of 2 units. And then, of course, we already talked about this. This is the tricky one. Shift right 3 units. Okay. Again, your horizontal transformations are independent of your vertical transformations. So it doesn't matter if you shifted these around. What does matter is that you do any stretches in the vertical direction before any shifts. Okay, next question is number 7. I'd like you to read that question over and underline anything that's important and what it is that we're trying to find. Play the recording when you're ready. Okay, so hopefully you took time to read that through and maybe even make a diagram of what's going on here. Cable hanging between 2 poles. Just kind of envision something like that, maybe like a telephone wire. Okay, so very flat, and we want to know the lowest point on that cable. So wherever that point is right there, that lowest point. So the minimum value of y has to do with the axis of symmetry. So if you envision your axis of symmetry cutting down there, the axis of symmetry, x equals negative b over 2a. That'll always tell you the x-coordinate of the vertex. So let's do that math. X equals negative b, so a negative 0.138 all over 2a. Okay, so when you do that math, you get 34.5 as the horizontal distance, okay, the x-coordinate. But we want to find the y-coordinate, so now you do a substitution of that x-coordinate into the function. And again, pop that into your calculator, do that math. Play the recording when you're ready. And it comes out that it's 17.62. We're going to the 10th. Let me get accurate to the 10th. 17.6 feet above the ground. Okay, our next question has to do with an average rate of change. Okay, so in this problem, we are, I'm not sure why there's that little bit of highlight hanging out there. Average rate of change, think about slope. Okay, in problem 8, I'm going to find the slope between those 2 points. Okay, and we want to find the x and the y values. Okay, these are our 2 x values, and I want to find the y values. So maybe we can make a little table. First, I'm going to look at the first function, f of x. Okay, so the x coordinates that are significant are those 2 points. And I want to find the y values by substituting in. Okay, so I'm going to find the y values of each of those 2 x values. I'm going to sub in -2 and do the math. Okay, so -2 squared is 4. 4 times 3 is 12. 12 plus 5 is 17. Again, you could use a calculator if you need be. You could look at the table on your calculator if need be. Okay, again, I'm subbing in a 4. 4 squared is 16. 16 times 3 is 48. 48 plus 5 is 53. So now I've got the y values, and I'm going to find the particular slope. Okay, so if you think about slope as your average rate of change, slope is the change in y. So I've got 53 minus 17 over the change in x. So 4 minus -2. So the change in y, 36. The change in x, 6. So the average rate of change for this particular function is 6. All right, and now we need to find the average rate of change for g of x. So again, I'll make a table. Just trying to organize it so you're able to follow these ideas here. The g of x function says -2x plus 7. It's a linear function. And again, we're going between those same 2 x coordinates, in between those 2. So to find g of x, sub in your -2, find the y value. I'm going to go through this in a little detail because last year students said, I couldn't figure out what you were doing in the video. So let's make it clear. I'm subbing in a -2 into this function. -2 times -2 is 4. 4 plus 7 is 11. Now I want to find what's the y value when x is 4. -2 times 4 is -8. -8 plus 7, -1. All right, at this point we have the information we need to find the average rate of change of the g function because we have how much the y and x change. So again, we'll call this our second point. So y2 minus y1, -12, over x2 minus x1, 6. Okay, and it came out -2. That should be no surprise to you because the slope is -2 of this linear function, right? Okay, and I'm guessing you could probably figure out how to do this second one given a little bit more time. All right, last question we're going to look at is on your eMath quiz review packet. So skip ahead to Unit 6 quiz review, and we're going to skip down to question 5, which asks about focus and directrix. Okay, we're given some information. We haven't talked about this in a long time, but it'll come back to you. Has a focus of 3, 9. That's a point. It has a directrix whose equation is y equals 1. That's a line. Okay? And the relationship with any parabola is all the points are equidistant from the focus and the directrix. So if you can imagine, I'm going to make a sketch down here, and if you can make a sketch for any of these problems, That is the one key step to nailing these. Okay, just relating the focus and directrix. So let's make an axis. Don't need a lot of space below the y-axis. Losing my mind here. I put y on the x-axis. All right, let's get that right. Okay, so go ahead and put in a dotted line where where y equals 1. Okay, so that's what we call our directrix. And now plot the point 3, 9. And that's what we call our focus. So all the points have to be equidistant from the point and the line. So that must mean the curve must have a vertex that's right in the middle. And then it must curl around that focus point somehow. Okay, so the parabola looks something like this. Okay, so we now know relatively where that vertex point is, and now we can find its coordinates. Okay, has to be equidistant from the focus and directrix. So that's why it curls around the focus point. That's our focus. This is the directrix. So what are the coordinates of that point? Well, it has to have the same x as the focus, so that gives us a pretty good clue that it's a 3 for the x. And the question is, well, what's the y? So why don't you do a little figuring, find out what the y is, then play the recording. So hopefully you realized, hey, it is got to be equidistant. Well, it's 8 units between 1 and 9, so I have to split the difference. There have to be 4 units down to the directrix, 4 units up to the focus, and therefore that coordinate is 4 above the line y equals 1, so that y coordinate is 5. There's our answer. It's also 4 below the point 39. Thanks for watching.